Hello and welcome everyone. What we want to do in this anticast right now is jumping more or less right into shellcoding and producing a simple shellcode for adding a privileged user to our etc passwd. Of course, as we only have around an hour, we can only cover some topics, and I might have to go a little bit faster through them. In the real or in the complete training course, we will take much more time on that. So let's see if this is working. Ah, yeah, it works. Awesome. So chapter 0. Welcome everyone. Who am I? I'm Marco. I do IT security for quite some time already. It's a lot of years in there. I did some infrastructure, web pen testing, low-level stuff. So I've seen already quite a lot, and I always liked shellcoding and also assembly, looking into exploits and stuff alike. So the next 3 topics will be about assembly, generally about shellcoding, and why we have chosen x86-32. An awesome matrix picture, so you know how assembly looks. So as I already said, when the question arose from Brian, assembly itself is like the last language for mortal human beings to learn if you want to talk to a computer or some sort of hardware, right? The next step would be binary. And well, although I do that stuff, the computer thingy for quite some time, I cannot really write binary constantly flow. Assembly itself is close to the operating system or / to the CPU and to the hardware, and we can directly use it to do things. The other things we discussed as well already, that it gives us a better understanding how things are working. Assembly is not that hard. It's not that hard to read and write, especially if you think about like nested code in one line or something like that. In other languages. However, it becomes pretty quick, very complex and hard to manage. Although there are some sort of macros and things you can do. Imagine that for a simple program like printing hello world or hello assembly world, you already need, let's say, around 10 to 15 lines, maybe in assembly to do it properly. You can do that in Python in just 1 line. Right. Yeah, and debugging pure assembly is actually quite some fun, and you learn a lot. Plus, some results might be quite surprising if you do things and make errors and you recognize what has been wrong. Shellcode, so as I said, shellcode is not shell scripting, and I say that by intention. Because in the past, it happened to me several times that people were coming and saying, oh yeah, that's nice. I also like to write a bash script. And I was like, no, not exactly. That's not what we are doing, right? So what we are doing is we're taking the opcodes and give defined or specific instructions what a program or the CPU has to execute in our process. Well, why should we do shellcoding as well? Because it's pretty low level and it's also quite cool. So you can go somewhere and say, hey, look, I'm a shellcoder. Maybe. Never tried that. Maybe it works. So we discussed that, why you want to write your own shellcode, how things are working. Maybe you don't like the MSF Venom code or it's not working anymore, because AV and EDRs are already recognizing them. So you might want to write some custom shellcode, which is exactly doing what you want. And you want to build up, a foundation, for instance, in reverse engineering or in binary exploitation. The x86-32 architecture is already let's say, not the most used architecture anymore when it comes on PCs. Nowadays, there's usually 64-bit. So, and then there's also ARM, which already started to take to attack the computer or notebook and workstation area. And so, why do 32-bit? 32-bit is still quite interesting, first of all, because you also can use such instructions and also the registers in 64-bit mode. Then there is still software coming in 32 bits. And the concepts, techniques, and stuff alike will also work on other architectures. Of course, it's not the same instructions. For instance, if you compare, or usually not the same instructions, let's put it like that, there are instructions which are the same. But what will be usually or always be the same, the concepts, the ideas, and the techniques we can use in shellcoding plus exploitation, right? Now we do a quick overview of shellcoding, or what's important in regard of that. We will talk about the registers, some basics for assembly. We will talk a bit about strings and a bit about syscalls. When it comes to this sort of processor, so the x86 32-bit Intel processor, we have like 6 general purpose registers and 3 special registers. This CPU has much more registers, but like MMX, and really depends also on the version of your CPU. So those are not all registers. There are some more, but those are the ones, let's say, which are the most important to us. As you can see on the left side, which are the general purpose registers, they have also special names, and they do have also special, let's say, uses with certain instructions. However, all those registers can hold all sort of values, like 4-byte, 2-byte, 1-byte values. So we can use them for storing all sorts of data. On the right side, you see 3 special registers, which is ESP, which is the stack pointer. We won't go too deep in this cast into the stack pointer. So if you don't know what a stack is, just imagine the stack as something where you can store data, which, let's say, grows if you want, or moves in a certain direction. Then we have EBP, which will store, which is the frame pointer and also has address of our beforehand function. And then there is EIP, which is the instruction pointer. And the instruction pointer usually points to the next instruction to execute. So if you have ever, let's say, accidentally or by purpose crashed a program with the classical A's, let's say with 2048 A's, and you have overwritten a classic stack-based vanilla overflow, you might have ended up with 41, 41, 41, 41 in EIP inside. And well, the reason for this was that the return address for the jumping back to the former function was overwritten with your A's, and then it tried to execute, but as this address is not a valid address, the program crashed. So all of those registers are interesting, and we have their meanings and their workings, and well, are important. Now, when it comes to the registers, as I already said several times, we are now at 32-bit. And so our maximum size for addressing is 32-bit, which equals to 4 bytes, right? Because 8-bit is 1 byte. As you can see, there's also 16-bit addressing, and there's also 8-bit, high and low. So what we can do now in the 32-bit mode is address certain registers, not only with 4 byte, but also with 2 bytes. And in the lower part of the register, we can also access the high 8-bit and the high low bit. This might not seem very interesting right now. However, when it comes later to assembly and shellcoding, it's very important, because addressing correctly the registers with also the correct sizes of, for instance, immediate values we want to store is very important, for instance, to get rid of null bytes. Of course, it also has other reasons, like if you need a special technique to store a certain value, or if you simply want to save space, right? There's a difference. If we would now look at 64-bit, we could also address the 8 bits for the source and the destination register. However, on 32-bit, this is not possible, right? Though, so that's, let's say, an exception on the 32-bit. Let's talk about some basic assembly instructions. XOR is a Boolean instruction, and for shellcoding, what's important here for us is that if we XOR the same register with itself, it will give us a nulled register. So why is that important? Because so if you write assembly code and you start with a new assembly program, the chances are very high that those registers at the start are nulled. But if you want to exploit a program, you have a bug somewhere in the program, and the chance is pretty high that this register has some sort of data. Now, we have talked about the addressing of certain values into the registers, like only putting their 8-bit, or just putting their 1 byte. Now imagine we want to put there only 1 byte, and we need this 1 byte, but there's another value in there already. And if you just we replace 1 byte, we get a completely different value. So rule of thumb is that you always want to have your registers clean. Right? If you're a bit more intermediate or advanced, you of course can adjust your shellcode to your exploit, and then you also know which register behaves like which, so like which state it is, right? And then you probably don't need that extra XOR instruction. But for beginning, we always XOR. So quite important one. Besides of that, XOR is also pretty much known for some sort of encryption algorithms where it's used. And even there's even a simple one for XORing where just 1 byte is always flipped and then the next one. So this will also, during our course, be interesting for a simple encoder and decoder. And yeah, I think that's it for now for XOR. Then we have MOV, and MOV stands, I think, even in the manual for move. However, my observation is it's not move, it's more copy. So what we are doing here is we are copying a value from one register to another one. And looking at this table there, there's one very important thing to know when it comes to the x86 architecture. It's little endian. And what's also interesting or important is that the syntax you can use is sometimes, let's say, at the beginning a little bit confusing, because if you're using Intel syntax, that's the syntax we see here, then the source and destination is exchanged. What does it mean? MOV is our instruction for copying a value. And then we have EAX. So you might assume that EAX is our source. However, it's not. It's the destination register. And then we have the source. So that means what that instruction is saying is copy over the value of EBX to EAX. In our scenario here, we have before the copy, so in the next line, we have let's say some numbers, so hex number, hex, and then 1, 2, 3, 4, 5, and so on. And in EBX, we have coffee babe. As soon as this instruction is executed, we have in both registers coffee babe. So if we execute a morph, it's not really moving in a sense like the value is moved out of EBX to EAX. It's more copied over to EAX. Morph is one of the most important instructions. You will basically most probably use it in every shellcode, and yeah, it's let's say crucial. Then there's push. Push is placing a value on the stack. We talked a little bit already about the stack, not going too deep into there. What we can see here is that the register EAX has a value of 41, 42, 43, 44, which is basically A, B, C, D. If we would look it up in the ASCII table. And as soon as we execute the instruction push EAX, this value of the register is placed on the stack. So now we have that value on the stack. Why do we want to do that? Well, we cannot hold always all values in the registers. Maybe we need some more data. Maybe our, let's say, for instance, we come later to that about strings. Strings like, let's say, a file name like etc passwd, so a path name in that case even, does not fit in a 4-byte register. So what we want to do is placing the string on the stack and then later getting the address, so the pointer to it, back into a register. And yeah, so we use it as storage. We cannot only push registers, but also immediate values. Well, this is just an example. So we don't need to, let's say, set a value in a register and then push it. We can simply say, okay, I want to push that value onto the stack. And this can be done like that. You can, so usually you push on this architecture 4 bytes, and this makes sense to keep also the stack aligned. When it comes to push, you could also push 2 bytes, but then the stack pointer is not increasing for 4 bytes, but 2 bytes in that case, if you push a half word. And this might end up in issues. Pop is the opposite of push. With pop, we copy a value from the stack and place it in a register. Now, the stack has a so-called stack pointer, that's ESP, and whatever value is there, where the stack pointer is pointing to that moment, that value is then placed in our register. So with that example, the stack pointer is pointing to a value which has our A, B, C, D, 41, 42, 43, 44. And in a moment we are popping that, this value will pop up in the EAX. However, this value is still on the stack, just the stack pointer has moved and will point now to another value. Okay, I thought we do a little demo here, so you can follow me in a debugger session through what I just talked about in regard of the assembly instructions. For that, I will change over to another machine, and we do a little hands-on here. Let's see, where is this machine? Okay. I hope you all can see the machine. Now we are in our session, and I've created before our cast a file called instructions. It's that file over here, instructions ASM. Let's open them up. Or let's say, we get rid of that. I'm so not an Ubuntu user. I don't like that. I just move that over. Do this. Okay. Let's do it in Vim, so we have a bit more of colors. Yes. So, and this is just a very simple assembly program, which will demonstrate some of the instructions we have talked about. In the first line, well, actually now in the first line, we have bit 32. This just tells our assembler, which is NASM in our case, that it is 32-bit code. The global start announces that there is a label called _start. This is quite important, and we need that. I've placed here some knobs. I have not talked about knobs before. You most probably heard it already. Knob stands for no operation, which is sort of correct in the sense of that it's not doing something exactly to your program in the moment, besides that it's using a cycle. So knob is just doing more or less nothing for one cycle. I like to use those knobs in example codes and alike, just as like boundaries, or when I debug some things. So just placing some instructions which are not changing anything to remember me, okay, here's maybe something other coming, another section coming, or stuff alike. Then we have our instruction in regard of moth. Here we are placing a value into EAX. Afterwards, we are XORing EAX, placing something in EAX again, pushing that value, pushing another value, and popping two values down. Oh yeah, we removed the new line. Maybe just for your, no. This one is a simple script we compile it with the NetWide assembler, NASM. We compile it in 32-bit and get an object file. And with LD, which is the linker, we're linking it also for this format for the I3386 and creating an ELF file out of it, so we can also execute a program. Right. For simple shell coding, or for shell coding, NASM would be usually enough because we get an object file. But from my point of view, there's some sort of, let's say, quality assurance you want to do. And this is, so it's very helpful if you also compile it to a program and test and play with the program and not just taking the opcodes from the object file. So with this compiled script, we just compiled a program we just had a look at. It's now created. Let's look at it. Instructions. It tells us it's 32-bit. LSB shows us the processor version. And let's execute it with GDB Jeff. So GDB is our GNU debugger. And Jeff is a pretty cool extension we will also cover in our course. There's also a Pwn debug, which is pretty cool. And there's also PEDA. I decided for Jeff because, well, I liked it the most. So we just started that one. Now we are in our debugger with Jeff extension. And in Jeff, we simply can say start. And Jeff has an auto mechanism if you started with a program to set auto breakpoints, which is already a great feature, which is not by default in GDB. And let's do that. Now, because of the increased font size, we don't see the everything perfectly. I think I scroll a little bit up for a moment. And what we see here is now that we have a breakpoint at the beginning of the program. And we see here our registers and their values. Now, as I said at the beginning, our registers are O's, so zeros all. Now, you might wonder, what's about this one and this one? And if you recall, we have ESP, which is a special register, which is the stack pointer. And the other one is EIP. Talking about the E is usually extended or extension. If you're probably aware, before 32-bit, we had 16-bit. And if you will just remove the E, you would have the 16-bit register, which was also the name on a 16-bit architecture. There's, by the way, a question to the crowd. Maybe someone want or can answer it. Maybe we do it later after we have finished all, which is your 64-bit also running in a 16-bit mode? Just food of thought. Now, back to the talk. So ESP is pointing to the current, to some value. And this all here is our stack. Right? And you can see, although we have just compiled some program, there are already a lot of values on the stack, which is quite interesting. And we are here, we have another arrow for that. EIP points to our next instruction. I will scroll down a bit, and we see here that our next instruction is the so-called NOP and has the opcode of 90. Now, let's execute that. Basically, nothing happened, right? Makes sense. There's no change in the registers up here besides EIP, which increased for 1 byte because NOP is a 1 byte instruction, 1 byte cycle. And so we had here +1. This is what will happen again. And now we are at our first instruction, which should do a little bit more. And if you compare, EAX is 0. Let's execute. And we have now this value in EAX. So we have created a value there. Our next instruction is XOR EAX EAX. And as you remember, if we XOR something with itself, it will result in a null. Let's do that. So XOR EAX EAX. And look up again. EAX is 0 now. So what have we done? We have first created a value in EAX, and then we just nulled it. Next, we will create a value again, or place a value with mof EAX, and then hex coffee. Now we have that value, the coffee value in EAX. And what we do next is we will push that value onto the stack with the push instruction. Let's do that. And as you can see here, now on the stack, we have hex coffee, which is, and the stack pointer is pointing to that value. If we scroll up a little bit, we see here our coffee, hex coffee in the EAX, and we also see here in the ESP register that the value here has changed, so the address, and the address is pointing to that value, hex coffee. We push another value. That time we don't push a register, but an immediate value. You see again, there is a change. We have now hex babe in here. And our next instruction will be a pop. And with pop, we will take the value from the stack. We're not really deleting it from the stack, but we will take the value. The stack pointer will change. and we will store that value in the specified register. Now let's compare that. In EAX is right now hex coffee. Let's execute the pop EAX. And after the pop, the value hex babe should be in the register EAX. Now we see we have an EAX hex babe. And let's now pop something into EBX. We see our stack pointer is here right now. We see hex coffee. Let's execute. And we have now this in our registers. By the way, the command I'm just printing here in Jeff is stepping for single instruction. And this is pretty helpful as, well, let's say my most favorite command besides break, start and kill in GDB Jeff, just for to go for another instruction and go for another instruction and so on. Okay, this is the instructions part. We will just quit Jeff and go back to the slides. Give me a moment. Okay, there we go. Nice. Strings. So we need strings, as said, simply because, well, we don't want only push some numbers or some binary stuff or whatsoever around in programs. As humans, we also like to read text or need text. And for this, we use strings. In our current example, we need strings at least for two things. One thing is the path name, etc passwd, right, which is a string. And the other thing will be the entry for passwd. To do that on a little endian architecture, we need to reverse the string before we push it. And also, we want to convert it to hexadecimal. So string reverse is actually pretty simple. Let's assume we have some word, which is called word. And on the little endian architecture, the first letter would has to move to last position. If you look from that, if you look from here, the second to the second one, the third to the one to before of 2, and this is for the last byte. Afterwards, we simply convert this value to hexadecimal. And of course, we can do that by hand, for instance, by looking into the man page, man ASCII. And if you've never done that before, you definitely should, and do it by hand and converting things to get used to it a little bit. But of course, this approach is quite error prone. So we will later use some simple Python scripts, or you can even do that with some Python one-liners. Let's see if we have enough time for the strings demo. I think we will just skip that because we will have the strings anyways in our final shellcode demo. Let's talk quickly about syscalls. Syscall is an abbreviation for system call, and this is giving the operating system the command to do something. So system calls are Unix operating systems, which includes Linux, sort of, although Linux is not Unix anymore. But Linux and Unix operating systems are based on syscalls. So for instance, if you want to open up a file, to close again, write data, read data, create a socket, and there are even system calls for rebooting. If you want to do stuff like that or execute something, then you need a system call. The system call is stored in something which is called syscall table or system call table, and which is an address in memory. which can also be overwritten, but that's another topic in regard of, let's say, for instance, rootkits or, well, even for defense mechanisms. And those system calls are used when it comes to assembly, have numbers. And we can look up those numbers in files which usually come with your Linux or Unix operating system if you have installed header files. So that means every system call, like for instance, exit, has its own number. And this number, however, might change from operating system to operating system, and also from platform to another platform. Basically, using system calls is pretty logic and simple. And let's see. This is an example comparison between 32-bit and 64-bit. On a 32-bit architecture, Linux 32-bit, we have exit at the number 1. If we compare now with 64-bit, the syscall number is 60. Right? So this is what I meant about that things can change. And so you should know for what or for which architecture you're writing the shellcode, or for which bit size. We can also see here at the socket connect, accept, bind, and listen in regard of 32-bit, it has all the same syscall number, which is like a legacy thing. There has been a change, I think in kernel 4.3 or something, that there are also extra syscall numbers like on 64-bit for network operations. But before that, if you wanted to do a network operation on a older Linux 32-bit system, and for instance, writing a shellcode for that, you had always to use the syscall 102, which was wrapping up the operations you wanted to do, which made it a little bit more complicated, and the shellcode a little bit, thicker. And but it was changed in the kernel version, and nowadays we don't have to do that anymore. At least not if our target system is not that old. Here we have an overview about the registers and how we have to place our values in. This is very important. I've talked before about those registers, and EAX always takes our syscall number. So for whatever syscall we want to execute, we have to place that number there. Depending on how many arguments a call has, we have to place the values for those in the next registers. So the first argument goes to EBX, the second one to ECX, and so on. After a system call has been executed, and if there is a result, this result is usually stored in EAX. This is also very important for later we want to open up etc passwd, and if we open a file, we get a file descriptor back, and this file descriptor is then in EAX, and we have to use that and place it somewhere in another register so it can be used as soon as we want to write. This is a simple example how we would do that for exit. So usually what makes all the sense is open up man page 2 and then the call you want to do, which will give you the arguments you need and the description of those. Here we have just 2 registers we need, one for the syscall itself, which is EAX, and one for the status. I like to use as a return code 4, which is placed in EBX, and EAX gets 1. What you can see here when in regard of 32-bit is a simple command to find our file, our 32-bit list of syscalls and numbers. Okay, now Let's do some more practical things. I will switch over again to the shellcode box. Or will I? No, let me see. I won't. Let me explain first what we're going to do, and then we switch over. Let's do it that way. Yeah. So this here is shows us what arguments we need for opening a file. As I said, we use that usually, we use for that the main page. And if we are looking into open, our first argument is the path name and then the flags. The flags is the kind of how we want to open up a file. Afterwards, we need write. Write has 3 arguments. One is the file descriptor, which was hopefully returned by open. Then we need an address or a pointer to the buffer or the data we want to write, and then the count or the length of what we want to write. We also can use close. It's not really necessary, and it might really depends on it might save us some bytes if we don't know not using it. And in regard of the flags, I've prepared here something already. As you might know, if you open up a file on Unix operating system, you can do it in different with different options, right? So you can, for instance, say create a file or truncate it, open it read only, open it write only, stuff like that, or even append, which means open it in write with a write flag and don't delete the file or something, but change data. I have prepared already for that some hex code you see down here, which is hex 401, which gives us the correct flag we want to provide for our open task. Also, as we want to add a password for this new user, there's a simple tool which will create us an old DES password. And we have a tool called push string, which will support us in creating quickly some values for pushing on the stack or for checking values on the stack. Okay. What we want to watch out for, yeah, how does the string end? Are there some lonely bytes flying around? Do we have a new line? We are using the bad Adduser passwd ASM. So in our classes, we have there's a lot of bad shellcodes created, and it's usually the task of the attendee to fix that shellcode with the things which have been learned. Right now, I am the attendee, and I will fix it and talk about it during the fixing, what we are doing and why this makes sense or not. And I think we will start with that now. So I will share now the shellcode box. And here we are. There are already some files created in there, and we open up the bad Adduser ASM. Or let's say before we open up, maybe just show etc passwd. So for those of you who might have forgotten that, I don't think so, but let's just say it. That's the file where, let's say 20 years ago, the users with some extra data and the passwords were stored in. Maybe it was even 30 years ago. And then shadowing was invented, which made a lot of sense because etc passwd was readable for everyone. And so with shadowing, the passwords or the hashes or crypted passwords had been saved in another file, which was not readable anymore for everyone. So if you're like, maybe let's say a senior, you started to work on nowadays so-called IoT devices, you have definitely seen passwords in etc passwd. Nowadays, that's usually not the case. There we have one. We should remove that. This is from a former test. Let's just remove this. So our shellcode is not doing something it shouldn't. So let's go back here. Now, here we have the first entry is usually the username. The X shows that the password is in the shadow. Then there's the UID, the GID, which is the group ID. And then usually there's a more explanation about the name, for instance, of user or extra data. Then there is the home directory and the shell for login. So as we want to have a root user, it makes sense to copy that line, right? Because we want to have UID 0, UID 0. Now, let's open up our bad user ASM. And as you can see here, you saw that already, it's bits 32. At the beginning, we XORing the registers. And what you can see is there are already question marks. So question marks are not legit values here when it comes to NASM. So I try to compile that program, and NASM will directly tell us, okay, there's something strange going on. So let's go back into the program and let's think about that. We said that we want to open a file first before we can change it. So this is probably open. Let's say also we don't know anymore what the arguments to open are. So let's go over here, open up a man page with 2 about open. And we can see directly here the return code, which is an int, then the path name and the flags. So our 2 arguments. Also, we want to know what syscall number we have to use. So we open up another file in another tab. And we are looking for open. And we see that open is defined as 5. Okay, so open is 5. We have 2 arguments, which is path name and flags. Let's see what we can do here. As stated into EAX, we have to place our syscall number. We just defined it's 5. So let's say 5. We have here push EBX. That's interesting. I might leave that to the end as a question why we do that. And then we have 3 push instructions. This looks like ASCII. This line here will copy over the address of our string. So we have a pointer in EBX. So in EBX, after this instruction is executed, in EBX is now a pointer to whatever has been pushed before on the stack. We know that ECX was for the flags, and if you recall, we already calculated that, which is this. Int hex 80 calls an interrupt. That's very important. It's, without that instruction, the syscall is not executed, right? So int hex 80 is on the 32-bit architecture always is one of the things you need for executing the syscall. Without that, no syscall execution. Okay. Let's assume that this is good. Now let's take from exit something. That's, I think, not working because let's do it like that. Maybe just uncommenting this. Placing exit here. Okay, now I give this like that. And so what I did here was just for Let's try to compile this now and see what's happening. And so I don't want that other code behind that function is executed. So I just put an exit here. So let's do that. We compile it again, or try to compile it. Let's see if it does compile. It does compile. Now we can use strace. Strace is also a tool we will use a lot in that regard. And let's see what's happening. Okay, two things we can see here. First thing is, we really try now to open a file. And the program is not crashing during that. It's cleanly exiting with the code 4. What you might recognize is, and this is one of the traps of this class, is that etc passwd is not correct. So we have here a capital A. Now, but we need a lower W. So let's open up ManASCII and let's see where W is. W is here. So it's hex 77. So we just go back to our code and we see here it's the 41, which is capital A, and replace it with 77. Save it and exit the program. Compile it again. Tracing it. And we see now, awesome, the path is correct. We open it with write privileges and append. But of course, we get access denied because we're not allowed to open it in write mode right now. Perfect. So this part already works. This is pretty nice. So let's go further. Let's go back into our assembly file. We remove that and maybe, yeah, we should completely remove it. Now, as I said before, after open, what open returns, if it is successful, is the file descriptor of the file we have just opened. This file descriptor, or the return value, is always an EAX. So this question mark must be EAX. When it comes to write, we know that the first one is the file descriptor. Here's the data, and then the length. If we don't know by heart, again, we simply open up the man page of write. So we know that the first argument has to be an EBAX. So we simply place that into EBAX. And now we have the file descriptor in EBAX, which is correct. We are cleaning ECX and placing 4 into EAX. We know this must be the syscall. So let's verify if it is the correct syscall. And yes, we want to use write, and write is number 4. So we place write there. Then we have here some pushes. Those look a little bit strange. We most probably don't need them for write, because write does not need a null termination. Now we are maybe not 100% sure what's in here with those pushes. We will go to that in a second, but we know that into EDX there should be the length. So the length is most probably not correct. Let's try to figure out what those push instructions are. If you're closing the file, and there's a tool called string push, and a little tool for the class. And there's a method, I think I called it deck, and there's a file for file name. And what we are doing is, let me see. Yeah, we take this data, the push instructions, copying it over into a file, saving that file. And now with the tool, we tell it to, let's say, decode it. And I think, was it F? Let's see, push txt. Yes. Okay, nice. So now this one is now decoding our push instructions. And as a result, we get a hex string and the ASCII variant. And what we can see here is a mostly ready line for our shellcode text string. However, what we want to have also is a new line in that code. So we maybe want to add that as well. Let's think about that. How are we gonna do that? I think we can also do it with string push. Let's see. Yeah, like this. And let's say we use those values from here. Platform 32 user input might already do the trick. Let's put it in those brackets. In those one thingy things. Perfect. Now, after executing, the program will show us in right order the strings, how to push onto the stack. But we also want to have a new line. And to do that in a nice and easy way here, so we are keeping a line to 4 bytes. We will only we will remove something from the name, I guess. Maybe call it even so hacker. This password here was already created. You can create your own password with that tool. This password is simply hacker. And at the end, we put if you just would do it like this, the output would not be good aligned. You see here, we are missing a byte in the last instruction. So to be aligned, we just place here an X as a placeholder, which we replace with the hex value of new line in a second. So we get this one here. The X is hex 58. We simply copy that over. And let's copy. Open it up in our bad ASM code. And paste it. We shall not forget, after we have pasted it, to replace our placeholder with a new line, which is hex A. So it's not X anymore. It's new line now. And now the length is important. So let's see how many lines we have here. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. 11 lines. 4 is 44 bytes. So our length argument gets 44. And let's see, this is the last part we need to fix. Well, not the last part, but one of them. This is our exit call, and we know exit is as one. Return code is this one. For fun, we can even let's put a 3. Okay. Now let's compile that program and see what is happening. It compiles. This is already nice. Let's do a quick strace on it. Okay, looks good so far. So what we can see is that the program tries to open up the file, which is not working because we don't have the privileges for that. Because of that, the file descriptor is not correct, and it tells us bad file descriptor, but we see that it's trying to write that line, and we see our adjusted exit code with 3. So this looks good so far. However, let's have a look into object dump. Object dump helps us, or is one of the many tools, but it's a board tool with Linux, which made it pretty nice and interesting, which helps us to show the assembly of a program, and also different sections, a lot of things. We want to show us the assembly in Intel syntax, and let's execute that. And what we can see here are our opcodes. Here we have an offset, This is the opcode, and here we have our instruction for that. And here we have null bytes. So whatever you might have heard about null bytes, in the area of exploitation, null bytes might be a problem. So this is for two reasons. One reason is it might, depending on the function you are exploiting, just simply cut your shellcode, because the null bytes are also terminating strings. So for instance, if you would go for a classic vanilla overflow via a C function like steer copy or steer cat or whatsoever, if you're trying to input your shellcode via that attack vector and you have a null byte in it, as soon as a null byte is hit, doing the steer copy, your shellcode is cut, right? So if the program does not care about null bytes, it might not be a problem, because a null byte also is a valid instruction. However, it might mangle your shellcode in a way, or even result in a seg fault, because the instruction in regard of the operands is invalid. Long story short, we want to get rid of null bytes now. And to get rid of that, the most important way is always thinking about addressing the registers, or how to address registers and how to store values in there. Now, in this example here, what we're trying to do is saving a 1-byte value in a 4-byte register, which is EAX, hence the 3 nulls. As you have learned in the beginning about registers, there's also an 8-bit register, a possible way to address the 8-bit one, which would be 1 byte. So let's go through the shellcode and adjust the things. Here we have open. Open gets 1 byte. And let's change this 4-byte register to the 8-byte low. If we go back now, compile it, and do an object dump on it, we will see that this morph, that the register correctly changed, and the 3 nulls are not existing anymore. So let's do that for the other parts as well. We open it up again. Here we have a 2-byte value in this line. This is our flags to open. And 2 bytes are 16 bits, so we can address ECX also in 16-bit mode. For this, we just need to remove the extension. So read the E. And with removing the E, we have now 16-bit addressing. Let's scroll down where we have to change things as well. Here, we want to address 1 byte only as well. We can remove those here. Let's scroll down a bit. Aha. Here we have another one. So it's just a 1-byte value. So we will only address 1-byte register. And here it's the same. So it's BL, EBX, BL. Okay. Now let's go out of that. Let's recompile it. Let's have a look in object dump. Aha. Here's one. We forgot one. At the exit system call. And well, looks good besides of that. So let's go back into the program. And here we have to that, compile it. Looks good. Let's try to execute with strace. Should not work. Where's strace? Here's strace. Aha. And here's something wrong. And this is what's happening if you have another value beforehand in one of your registers you're using. In that particular case, it's X. So let's go back here. EX, XOR, EBX, compiling it. It's strace. Looks good now. Okay, what we are now missing is just the privileges. However, we will do that in a second. Now we just get out. I think we maybe run out of time, so I try to.
We are a little bit over, but this is a lot of stuff.
So how much time do I have? I think
how much time do you got left?
Well, let's put it that way. I think I'm finished in 10 minutes.
We might. Oh, whoa.
Why don't then I try to make it in 5?
Okay, let's see. Let's do the speed run on the rest of it for you. Yeah, go ahead.
Yeah. Okay. So I try not to explain so much anymore. So we just use that tool here now, and we getting our opcodes with that from what we have just compiled. We take those opcodes. We see that the opcode lang is 113, and it seems not to contain any null bytes. This is one of the tools we use in our class. We just take this, which are our opcodes and hexadecimal. We open up, let's say, something we could use for our exploit, putting in here the shellcode. So that we want to compile our, let's say, fake exploit. We call it fake exploit. We use a C program. We say it's for 32-bit. We compile it. Something's wrong here. Yeah, okay. Let's see, have we compiled our fake exploit? We have. Let's see if our fake exploit, what it's saying. Okay, looks good, looks very good. It's doing exactly that. And as you know, so normally we would use that in a, that's for instance, in a local privilege exploit to gain root, for instance. Now, as we have not combined it here with such an exploit, we have to give our program root permissions so we can use our fake exploit, right? That's what we do now. We change on root our fake exploit. Then we give it set UID flag. And let's see if it works. I hope so. We execute it. Oh, before that, let's say we just etc passwd and let us tell what is the last entry. The last entry is SSHD. Now let's execute the fake exploit. If everything worked, it should now be our new user. Okay, nice. So we have now so hacker in there. The password is hack3r. And to see if it worked, let's try to gain our newly created root account. So let's sue into so hacker, and I hope I get the password right. Yes, there we go. We are root now. So this was very quick and not even 10 minutes. And there's a lot more to tell about. There's a lot of stuff going on. I'm sorry that it took me more time to explain. And I hope it was nice to see.
No, I think, and that's, I was going to actually talk about this a little bit. If anybody wants to know more about, I mean, obviously I think some people are very, very interested. I'm in the chat. I'm, you know, virtually lynched right now. People are really upset at me for shutting this thing off. So, so apologies for coming in and making you go a little bit faster. Oh, see, Megan and I had the exact same thought at the same time. So yeah, people are upset at me about this. But if you guys want to know more, want a little bit of deeper dive on this, obviously we have a class coming up, or Marco has a class coming up on at the Snake Oil Summit on December 6th, I think it is. So there's a free registration. Just if you can go there and you can register and watch it for free. But if you really want to know more about this, definitely register for Marco's class, and you'll get a lot deeper dive into some of the stuff he was talking about here. So this was a lot. This was pretty cool. We were kind of listening to it in the backstage, and I was sitting here watching. It's like, whoa, I'm trying to keep up with all the stuff he's doing. But so obviously the community loved it. So Megan, what else do we got right now? I don't have time for questions, but go ahead.
since we've got Troy on, Troy is also going to be teaching a class. If you want to run through your class, Troy, and let people know about what you've got coming up at the Snake Oil Summit as well.
Yeah, I teach network forensics instant response. So the opposite ends of the spectrum of deep diving in the bowels of assembly language on an endpoint would be on the network side of things. So covering some foundational aspects of IR, but in doing network forensics in support of incident response engagements. So we look at everything from full packet capture all the way down to NetFlow, utilizing various different tools and techniques, looking at attacker techniques to TTPs of exploiting different types of network protocols in order to achieve their objectives, learning about those protocols and deep diving those network protocols, and then kind of getting into like the Zeek IDS technology, a deep packet inspection type technology, even doing custom Zeek scripting. So if you've heard of Zeek and kind of interested in Zeek, the class kind of goes through some Zeek scripting type examples in order to pull off some customization with that. And then the course ends with with a capstone that deals with a fictitious intrusion, from like initial access all the way to the attackers like achieving their objectives, or at least the student needs to determine whether or not what they did in that intrusion set. So, and then also I'm for the first time publicly I'm saying this. If you've heard, last year it was announced that there's Zeek for Windows. If you have Defender for Endpoint, right? You can actually get Zeek for Windows.
It's baked into it now, right?
What's that?
It's baked into it.
It's baked into right? Well, it's baked into it. So I'm actually gonna
it's Windows
releasing a new module to look into what Zeek for Windows like kind of exposes on from the network perspective, or from on the endpoint into like kind of delving off the endpoint into network, because we're gonna spend a lot of time with Zeek in the course. But kind of get a look for Zeek for Windows and do a compare and contrast. So and then those people that have already registered for my class on demand, you'll automatically get that updated module once that's added to the class. So looking forward to teaching it.
Yeah, let's create another scenario real quick here. So say you're sitting here listening to us and you're like, yeah, I might be interested in taking some of these classes, but I don't want to necessarily commit to purchasing a class quite yet. You go register for the Snake Oil Summit. And by the way, I would say, Megan, and Brian's not here. He's hiding backstage. But I think you guys can all agree. One of our more popular webcasts that we ever do is when John gets on and he rants. Yes. And he gets worked up, right? And so the name of this summit that we're doing on December 6th is called the Snake Oil Summit, and where John's going to just rail against a lot of the over bloviated marketing terms and things that are out there. If you're familiar at all, if you've been with us long enough, if anybody here remembers, by the way, I'd love to see this in chat. Does anybody here remember when we used to do the Sacred Cash Cow tipping webcast on an annual basis? That was essentially us going like, hey, look at all this marketing material from these EDRs that say we catch all 0 days. That's not true. So what we do is, it's kind of an extension of that kind of stuff. So it's going to be a lot of fun. You're going to hear a lot of people get really worked up over some of the marketing stuff that gets thrown in front of them. So let's say you're not ready for a class, still attend the Snake Oil Summit for free, because it's going to be some cool stuff in there as well. So with that, Ryan, Megan, what have I forgotten now as my first time?
The only other thing I wanted to mention is because, tomorrow's Thanksgiving here in the US. And then of course, Black Friday, we are having a Black Friday sale for our on-demand subscription. So if anybody is interested in that, it's like 90% off. I mean, it's like some crazy amount off.
Wait a minute. No, wait, what?
Because each individual class is $575.
Okay. I haven't been a part of this, so I don't know. So I wasn't consulted on the 90% discount.
Well,
okay.
We suck at capitalism. So
gave me a heart attack, man.
It's like, look, I'm not a math person, but it is a lot of money. It's $1,500 for the entire catalog. Currently, I think there's how many classes, Kyle? 28, 29?
27. Yeah. 28.
Something around there. 30 plus, actually, Brian. Thank you.
And mine's going to be on there very soon. They're doing the edits on it right now.
Yeah. So and if you get the subscription for 1 year, any updates to any classes that are already in there, or any new classes we add, you also get access to that, and you get 1 year of the cyber range. So just to let you know, we got a lot of new classes coming out. So it is a heck of a deal.
All right, we are 15 past now. I'm tempted to just yell at Ryan to burn it with fire, but am I forgetting anything? Marco, any closing words, any closing wisdom that you want to share with the people that are still hanging out, the 250 of them that are still here?
Closing wisdom. Okay.
Yeah.
But I'm sorry for that. I might look like
No,
a
it's
senior,
okay.
and I'm sort of but wisdom is nothing I've
You were in the
reached
zone,
my
Marco.
life.
Yes.
Yeah. Sometimes it happens. The demo gods were shining very favorably on
Yes.
you there.
Well, I want to say thank you very much. Thank you guys here from Anti-Siphon for giving me the chance to present it and also for the training. And I want to thank also the attendees. I hope you were able to learn something and I did not bore you to death. So thank you very much and hopefully see you at the training.
Yeah.
Awesome.
Well, we'll see you at the summit and the training. I think happy Thanksgiving to everybody.
Happy Thanksgiving, everybody. Yeah.
Happy Thanksgiving.
Happy tryptophan.
Yeah.
All right, Ryan, let's burn it with fire. Let's get out of here. I'm sick
Bye,
of sitting down.
guys.
Bye,
Have a good
everybody.